Greetings, ENGR1166. For our first video project, Group 15 decided that our topic of instruction will be in the statics field, trusses and methods of joints.
The method of joints is one of the many ways to apply different mathematics and science in studying the engineering and makeup of trusses in order to implement them.
Now to move on to the anatomy of a truss. A truss is a thin, long, straight member that is connected by joints. They are usually stationary and fully constrained with two equal and opposite forces directing along the member called the axial forces.
We will not be considering the weight or center of mass of the trusses, however. They can be considered in larger structures, but we do not need them for this experiment. Instead, we are only looking for the axial forces and the internal forces of the member that act on the joint.
The joints are key in understanding the truss structure. In this experiment, it can be assumed that the joints are pinned together, and that there is no moment as a result of this support. In this way, it can be implied that all the forces acting on the joint equal one force. In statics, to prevent the movement of the structure, the force is equal to zero. For our experiment and explanation of the theory, we will only be considering ourselves with a 2D representation of our structure. We will only consider one face of the structure when figuring out the summation of the forces on the members. In our experiment, we will make sure our truss structure best represents the calculations we will be performing.
Furthermore, our members in the experiment and in calculation are considered rigid bodies up to the point they break. This means that any deformation due to weight or strain will not be considered, but will be mentioned during the experiment.
In order to determine the individual internal axial forces on each member, it is important to know all of the forces acting on the structure. The first step is to see if there are any external forces acting on the structure, like a weight and on which member it is being acted upon. Typically, for simplicity, they act only in the y directions, up and down, but can act in any direction, typically. Next, you must find the reaction forces of the supports. To find these, determine the direction and use the three equations: the sum f of x equals 0, the sum f of y equals 0, and the sum of the moments around a point equals 0 to determine the magnitude. It is okay to not know the direction of a force or moment. Any guess will do, and if the magnitude you solve for is negative, and assuming you get it correctly, just switch the direction.
Once you find all of the external forces, to find the internal forces, you go joint to joint, hence the name joint method, and use the summation of all the forces acting on the joint. To do this, you will take any point forces acting on a joint and you draw forces in the direction of the members. Like before, it is okay not to know the direction, as long as you know that if your value is negative, it is in the opposite direction. You once again use the static equations using trigonometry when necessary.
A tip when looking for internal forces: start with the joints that only have two members. This makes it easier to solve for each of the forces without any unknowns. Also, use symmetry to your advantage, whether it's symmetry about a joint or a structure. Similar forces will arise. Finally, axial forces can arise in either compression or tension. While tension and compression is easy to show on a joint, to figure out whether a member is in tension or compression, simply observe its effect on the joint. If it points towards a joint, it's compression. If it's away, it's tension.
Now we are going to solve for all the members in the truss using the method of joints. For our experiment and demonstration, we constructed a worn truss structure using popsicle sticks.
The first step in solving for each member's axial force is to find all of the external forces due to the weight and the reaction forces. For our experiment, we are ignoring the weight of the structure as the sticks are relatively lightweight compared to our weight. Our weight has a mass of 200 grams, which translates into about 1.96 newtons. We are placing the weight in the center to simplify our calculations.
The next step will be to calculate the reaction forces. The structure is 2D, meaning we will not have to calculate any z component of our structure. With our coordinate axis, y is down to up and x is left to right. The weight is acting in the negative y direction. Our two reaction forces are on each side of the structure. On both sides, we have a rough surface.
To find the reactions, we simply draw them using our prior trigonometric knowledge. After drawing arbitrary directions for the reactions, we, using the equation, the sum of f of x equals 0, to show that the x directional forces of the rough surface is equal to 0. Then we use the equation, the sum of f of y equals 0, to show that the y directional force at A, dubbed AY, plus the y directional force at I, minus the weight, is equal to 0.
The first step in solving any truss problem is to find all the reaction and external forces acting on the structure. We have two equations of motion to work with. Sum of f of x is equal to 0, and sum of f of y is equal to 0. In the structure, the reaction forces at A and I have reaction forces. At A, there are two forces, A of y and A of x, and at I there's only one. In the x direction, there's only A of x, so A of x is equal to 0. In the y direction, there's A of y plus I of y minus the weight. The weight is equal to 1.96 newtons. Rearranging the equation, it's A of y plus I of y is equal to 1.96. To solve for either A of y or I of y, you set the moment on either one of those points. I'm going to pick A and set that equal to 0. And we have the weight, which is at 0.26 meters away in the negative direction, plus I of y at 0.52 meters away. Solving for I of y, we get I of y is equal to 0.98 newtons. Going back to the original equation, we saw that A of y is equal to 0.98 also. Now that we have the external and reaction forces, we're able to take apart the joints and study the internal forces that act on each of the members. We're only studying A and B for the sake of time. At A, we have the external force AY, and we replace the members AB and AC with forces. We chose the directions of our forces AB and AC arbitrarily, but we tried to reason it out. AB has to go down to counterbalance AY, and AC has to counterbalance AB, so it goes into the positive x direction. Using trigonometry, we're able to relate each of the forces using the sum of fx and the sum of fy equations. AC minus AB cosine theta, and AY minus AB sine theta, with theta being found using trigonometry because each of the triangles are equilateral. Solving for the equations, we're able to find that AC is equal to 0.658 newtons in the tension, and AB is equal to 1.13 newtons in compression. We're able to find this because AC is going away from the joint, meaning it's in tension, and AB is going towards the joint, which means compression. Now that we have force AB, we're able to look at joint B, and we're able to solve for the joints BC and BD. Like before, we took apart the members. Using trigonometry and knowing that it's an equilateral triangle, we're able to find beta, which is equal to 30. Using the sum of fx, we're able to find that AB sine beta plus BC sine beta minus BD equals 0. And in the sum of fy, AB cosine beta minus BC cosine beta is equal to 0. Solving for BC and BD, we're able to find that they're both equal to 1.13 newtons, but BC is in tension and BD is in compression because of the way that their arrows are pointing. They are positive, so that we knew our initial assumptions are correct.
Go. In conclusion, the method of joints is a simple and effective way to find the internal forces on all members of the joints.
This method is crucial when determining what type of structure an engineer will use for a project, or what materials you will use for the structure.
That being said, I hope you enjoyed our video. Thanks for watching.